haven't done my Babylonian bit. Looking for some sign of recognition of, as I mentioned, the Babylonians. How many degrees are in a circle?
360.
Okay. Why?
Because 360 is like a full rotation.
Yeah, why is it not 400?
Isn't it because it's easily divisible or something like that?
Yeah, something like that. But that goes back to the Babylonians. Babylonians recognized that 60 was an important number. They attached, by understanding, they attached some religious significance to the number 60. And because, and getting to what Caleb just said, there are a lot of numbers that go into 60 nicely. It's divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. So it's divisible by a lot of nice numbers. They also recognized that the equilateral triangle was special. There was something in the purity of it that they liked, and so they assigned 60 to each of these angles here, which we now call degrees. And so a triangle is 360 degrees, or sorry, a triangle 180 degrees. And if I take 6 of those triangles, I've got 60, 60, 60, 60, 60, 60, or 360. So the whole reason is 360 degrees. Mathematically, it's divisible by a bunch of numbers, and also that's what was established several thousand years ago, and the people didn't change that until at some point, I believe it was sometime in the 1800s, there was a big movement to try to get as much human invention out of math, to see what actually comes in nature. So they developed a different way of doing angles. If you take a circle here, as Grace mentioned, if we have half the diameter, that is the radius. All circles will have a radius. So imagine I got a circle here, and I've got a piece of string that is the length of the radius. And then I take that string and I wrap it around the outside. So I wrap it around that far. So that arc length right there is the radius. It's the same as this length right here. If you do that for any circle, this angle is always the same. Take the radius of the circle, wrap it around the edge. It will, I think the proper term there is sub 10. Is sub 10's the same angle? And they said, well, this seems to be natural. This is not man-made. This is just something that seems to show up for every circle. And they said, this is 1 radian. So it's just a different unit for an angle. And you can go one step further is, well, how many radians are in a full circle? Well, how many times can I wrap the radius around the edge of a circle?
6 times.
Say it again?
6 times.
A little bit more.
Is it 12?
No, not that many.
Okay.
Well, we're talking about the circumference of a circle here. What is the formula for the circumference of a circle?
Pi times
And the diameter is twice the radius. So the circumference of a circle, pi times the diameter is right, or 2 pi radiuses. So I can wrap the radius around 6.28 something times. So it's 6 and a little bit. So the number of radians there are in a circle is 2 pi. So 2 pi radians equals 360 degrees, which equals 1 revolution. So we have sort of a language here in which we can talk about things, how things rotate. Questions here? All right, so let's take a look at kinetic energy. I'm about to ask the question, so if you need to quickly check your notes. I'm assuming those not checking their notes already know it. What's the formula for kinetic energy?
Oh, 1/2 mv squared. 1/2 mv squared.
Say it like you mean it.
1/2 mv squared.
That sounded the same to me. I guess you've been it the last time. All right, so we have the formula right here. Unison would have been really cool. But if I have an object rotating, so let's say that I've got some object right there with an axis right there at the middle that's got a hinge at the bottom so this thing can rotate freely around. Well, this object would have a mass, so imagine I've got a ruler here and it's just rotating around like that. How do I determine the kinetic energy of an object that's rotating? Because this part here is moving faster than this part here. Linear speed, the v, the speed here is greater than the speed here. So the speed of what point would be a nice estimate for now? We take that as the speed, or that is the speed, or that is the speed. What bit do we use to try to figure out this kinetic energy of an object that's rotating about some point at the end?
Would you like average about it? Would you like find 2 separate points and then average?
Or the middle?
Sure.
Okay. Well, if you say 2 separate points, if you did that point and that point, that probably would not be it.
Like if you did like the highest and the low.
Okay, that would put it in the middle. All right. So if we found the speed in the middle, that is an estimate. So this would be approximately 1/2 times the mass of the meter stick times the speed of the middle. I'll just put average speed squared. We could come up with a better estimate if we actually thought of this as 2 objects. So we got this, so the top half, just call this part 1 and part 2. So that we get a better average, since I cut it in half, this is the mass of the meter stick over 2 times, we'll call it speed 1 squared, plus 1/2 times mass of the other part, v2 squared. So if we looked at just this part and that part as 2 separate objects, we could break it up into 4 objects. Think about it as I got 1, 2, 3, and 4. And so 1/2 times, broke it up into 4 objects. V1 squared plus 1/2 m over 4 v2 squared plus 1/2 m over 4 v3 squared plus 1/2 m over 4 v4 squared. Now this is going to get really long, so it would be nice if we had a shorthand way of writing this. And of course there is. If I'm adding the same stuff up over and over again, then I can use that symbol right there. This is a capital sigma. And that just means I'm going to add up all the stuff that comes after it. I got a 1/2 times, I'll just shorten it to mass 1 times v1 squared, I equals 1 to 4 in this case. So this is the shorthand notation of writing all of that out. Where m sub I is just, in this case, the mass, total mass divided by 4. Now we get a better estimate if we break it up into 8 things, or if we break it up into 16, 100, 1,000, 1,000,000. The more parts we break it up into, the better it gets. Obviously, to do this by hand would take an incredibly long amount of time. So what we're gonna do here is, well, let's just explore that. So the kinetic energy of something rotating little r there for rotational kinetic energy is the sum 1/2 times whatever that mass, we'll do it m sub I v sub I squared, where I goes from 1 to some number, some large number. Eventually we'll take it to infinity. Not yet though. Now, I had something of uniform density over there. I broke it up into even pieces, but we're not guaranteed that every tiny piece will have the same mass. So I'm going to leave that as m sub I. But I do have a constant here of a 1/2. That 1/2 can be factored out. Every term here has a 1/2 in it, so I can bring 1/2 out. So that is 1/2 times this sum of m sub I v sub I squared. See how much simpler this looks? We're not to the simpler part yet. Well, there's a relationship between, there is something that is common to everything here. Not the linear speed. Linear speed changes. This is faster than this is. But the angular speed is the same. So I want to somehow work angular speed into that. I know that the arc length here S for arc length is equal to the radius times the angle. And this angle here is in radians. And just do a quick check here. If I do an entire circle, my arc length is the circumference. If I look at an entire circle, which has a formula of 2 pi r, and that should be equal to r times the angle, and an entire circle is an angle of 2 pi. So it works there. So I have this S, arc length is equal to r theta. Now, if I think about this thing rotating, I got some point right here that's going to rotate through some angle. It's going to travel a distance. So it's going to travel some distance, r delta theta. It's going to do it in a certain amount of time. Well, what's distance divided by time? Nope. So we just said it? Speed. And angular distance divided by time?
Angular velocity, angular speed.
Angular speed. So we have this relationship here, that V equals R omega. So what I'm going to do is I'm going to make that substitution over here. So that's 1/2 times MI times R I omega squared. Now, R depends upon where we are, how far we are from the axis. Omega is the same for everything, so I don't need a subscript. Matter of fact, that can factor out. I'm left with 1/2 omega squared times the sum of all these MI/RI squares. Now it should be obvious, or not. Questions to hear before I put the final stake into it? This right here is the moment of inertia. Bless you. So my formula becomes rotational kinetic energy is 1/2 I omega squared. Now, we could have gotten that already, because we transliterate regular kinetic energy as 1/2 mv squared, and these are just the rotational analogs of mass and speed. And I need the book and 2 props here. I'm gonna pause this, I'm gonna go get. All right. Now, you might be looking at that and going, that really doesn't make it any easier. I'm supposed to add up a whole bunch of terms here. It don't. There we go. On page 138 of the textbook, for certain common shapes, they have already done it for you. Right there. If you look at any beginning textbook in physics, they're gonna have some chart like that. So for this one, if I have a stick rotating about the end, so this rotating about the end, the moment of inertia is 1/3 ml squared. M is the mass of the whole stick, and L is the length. That is the. Let's see if I can do that slightly neater. Now, the reason I put capital letters there is just convention, is that when you're talking about the whole thing, you use the capital letter. When you look at part of it, use the lowercase. So if this is 2 kilograms and the length is 5 meters, the moment of inertia is just plug and chug 1/3 times 2 kilograms times 5 meters squared. Which is 16.6 repeating. That sounds about right. Units. What would the units be? Think about what we multiplied.
Kilograms?
Is it kilograms? Not if you're stopping there.
And that sounds meters squared. Kilograms times meters squared.
Yes. Kilogram meters squared. There's unfortunately no one-word unit for it. So if I take a track, that is not going to do. Oh, that's what that's about. All right, so exploring moment of inertia. I have 2 objects here that have the exact same mass. The difference between it is that this has most of the mass on the outsides, and I don't know how well you can see that, but it's blacked out here and it's see-through down here. The other one is the opposite way. It's see-through up here, but black down here. And the black part is where they've got most of the mass. So I got the 2 objects here and different mass distribution, same mass. But they should have different moments of inertia, because the moment of inertia deals with the mass and how far it is from the axis of rotation. So if I just spin it about the middle here, or this one, most of the mass is towards the middle. It doesn't take much to get it to rotate back and forth. This one, on the other hand, hurts when I try to stop it, because most of the mass is on the outside. It's harder to get to rotate, and once it starts rotating, it's harder to stop it. And if any of you need to experience it, just raise your hand, I'll bring these to you, and you can see the physical difference between the two. Or you can just sort of partially raise a hand.
Oh, yeah.
That's with most of the mass right there near the axis of rotation. So, yeah, so you're rotating the exact same mass, the only difference is the distribution. So the blue one has a much higher moment of inertia than the red one. Anyone else need to feel it? Or just want to? Now, what are the implications here? I have two objects. And a second track would be very nice. All right. We'll forget the track and